Okay, everyone. So, how many of you have tried to finish this problem? I'm not going to ask you questions, so you can easily raise your hands, and it will have no consequences. But have you tried to finish this?
That one?
Yeah, this. We're going to finish it. So, if that's the way you're approaching the class, I'm telling you, be careful. You really need to. Yeah, right. Okay. Regarding the exam, I know that's all you're thinking about. So, as soon as we're done here, I'll email it to you. I know there's a way to do it on Canvas. Don't ask me to do that because I have no idea. We'll do everything via email. I'll send it to you. In the email, there will be instructions. You scan it, send it back to the TA. It's pretty simple. You have a little more than 24 hours. I'll send it as soon as I'm in my office, and I'll say give you until 3 p.m. tomorrow, something like that, just because I need to work around schedules here, mine and the TA's schedule. So it will be 25, 26 hours. That's more than enough. It is not designed to kill you on crazy calculations. I mean, if you want to kill yourself in crazy calculations, be my guest, but think twice before you start doing anything. It is designed to test your understanding and show me that you've understood the concepts, not to test you on algebra, because that's not the focus of this class. So again, think before you do it. You have more than enough time to do it. It's 4 questions. Yeah, more reference frame is better. Well, but they have to make sense, of course, and they have to be reference frames. So, yeah. Okay, so this problem here, you guys suggested to do it with respect to the center of mass, and that's what I've done. And I actually had it solved with respect to Q. That point we said it was probably more convenient, but let's try to finish it with the center of mass, just to show that it is not always wise to look at an expression like this one that we derived and assume that as long as one piece cancels out, my life will be easier. It's actually not the case in this particular problem. So in this particular problem, picking the center of mass means that that Q is that point C, right? We said that. And so this equation simplifies into, as we said, d dt in n of the angular momentum with respect to center of mass. So we indicate it with bar that is where it goes. G is inertial. H is with respect to the center of mass. It comes down to be equal to m bar. So we do everything with respect to C, and this piece goes to 0 because Q is r bar. So it looks better than that, but in the end, when you do the calculations, actually, as we'll see, it's the wrong way to use this tool, because you will be stuck with the 2 reactions at point B and A, and these will end up being not sufficient to solve the problem. So you have to go back to do something else to actually remove those unknown reactions. While if you do it with Q, which I invite you to do at this point because I don't know if I have time to do it both ways, you will see that they obviously don't contribute to M. You still have this second part, but the reactions go away. So it is wise to look at the problem 1 time, 2 times, 10 times before you make decisions that then you will have to pay later on. So this is not necessarily easier to use than this. That's my point. What it's easier is thinking about the problem. That really makes your life easier. So if we do it this way, let's see. Well, we have to find H. I really want to do it quickly because I would like to briefly touch on tensors today, which is one tool we need for rigid body kinetics. It's all stuff you can study on the book by yourself, to be honest. But okay, so if we do it with respect to that point, we have, well, this is the definition of H, right? Summation over I of R, I. I'm just going to use my notes a little bit because I want to make it quicker. Mi Vi in G minus V, this is bar, right? V bar in G. Okay, which in this case, how many masses do I have? I only have 2. So if you break it down, it's Ra minus R bar cross with M, they're all the same mass, Mv of point A in G minus B bar in G plus Rb minus R bar cross with M, same V of point B, as seen by an observer fixed in G, which again is an inertia frame. All this is only valid in an inertia frame, minus V of the center of mass. One more comment. Now, this is h. I have to take its rate of change and then find m. And to find m, you need to know what are the forces acting on each particle. Last time we said that, for example, for A, we have mg, force of gravity, and some unknown reaction that I'm going to call Na. There is no friction here, exerted by the ground on A. Is this sufficient? Is this the free body diagram of particle A of mass m? What else is there? There is some force along AB, right? We assume that for all these things that we are doing here, the third law of Newton is valid. Of course, that's always valid. But we also have the strong form. So there is some force here. Let's call it F. This is F on A by B that is there. So that would be the complete free body diagram, right? And this is pointing along that line, the arm, pretty much, AB. Now, do I care about that? When we derive this is the moment of all external forces. So you don't, because all those internal forces, they cancel each other in terms of the contribution to the moment, mq. So no, I don't care about this. So that's why I didn't have it there, but that's actually an error not having it there. That's not the proper free body diagram. It's just that this doesn't contribute. I don't have to care about that force when I compute my m bar in this case. Make sense? Okay, so without going through all the calculations here, I can do maybe a couple of steps, but then I'll give you what is the final result of this. What is RA? Where do you want me to write them? Maybe down here. What is RA? Real quick, at this point you should be pretty quick on this. That's the coordinate system.
L sine theta EX.
That's right. Big EX. We said we had two reference frames, remember, but at some point realized it's not really needed. So RB is, what is this? L cosine of theta EY. And then, what is R bar? You can either apply the definition of center of mass or notice that R bar is this vector that goes here, right? This is R bar. So what is that? Project.
L over 2 sine theta plus L over 2 cosine theta. Or no, EX. L over 2 sine theta EX plus L over 2 cosine theta EY.
Okay. L over 2 cosine of theta EX, that's what you said? Plus L over 2 sine of theta EY.
Would it be sine theta in the EX term?
That's right. That's what I have. Okay. So you can do it by just looking at the drawing there, or if you don't want to take any chances, what is R bar? What is the definition of R bar? Remember, when you're not sure about something 100%, just go back to the definition. R bar in this case is what? RA m plus RB m. Is that right? Yeah. Over 2m. So that's what you get. RA is L sine of theta divided by 2. Yeah, makes sense. Okay, cool. So if you don't visualize it easily here, just apply the definition. Okay, so if you start doing RA minus R bar, RB minus R bar, I'll leave that up to you. The other pieces that go in there are the velocities. Well, still not much that we need to say here. The velocity of A in G, I really don't have space here. What is the velocity of A in G? Let me write it here, then I'll erase it. VA in G. Well, RA is already expressed. L theta dot cosine of theta EX. VB in G is minus L theta dot sine of theta EY. And likewise, you can find the velocity of the center of mass with respect to an observer in G. because all the vectors are already expressed in a coordinate system which is fixed in the G reference frame. That's why I can do that. Okay? Fine. So you do all your calculations here, and in the end, what you get for H, let me see what I have here. I want to give you just the final one. There's no point in going through all this craziness. I have something that looks like, that's not the final one, this is the final one. Okay. It's actually going to be just L squared theta dot over 2 EZ. That's your H bar. You do it at home. It is just cross products. And just a sanity check, everything I'm writing in these vectors, these differences of vectors, is vectors that belong to the plane. So it does make sense that everything that I get is in the EZ direction, right? It will be all EZ, EX cross EY, EY cross EX, etc. Go ahead.
Do you not have to tell what reference frame H bar is expressed in, or M bar, because it's the bar?
Yeah. I'm sorry. Yeah. This is G, this is G, this is G, this is G, 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 G. Yes, thank you. Yep. That is absolutely right, because the velocities are in G. The positions are with respect to the coordinate system fixed in G. Yep. Okay, so that's your H. And then this means that your d dt do it. Just verify that that's what you get. There's really nothing special behind doing that. It's just a bunch of cross products, and at some point you will have sine squared and cosine squared that will give you that. So if I want to compute this part of the equation, well, what is the dt of that is L squared theta double dot over 2 EZ. That's it. That's pretty nice. Now the unfortunate part of this is that M bar. How do you compute this? Since we picked the point Q to be C, what I am going to do is compute the cross products of vectors between the vectors that go from point C to any of the masses in the system and the forces that act on those masses. So I'm going to basically have the vector that goes from C to A crossed with all the forces that act on A, of course the external ones, I don't care about internal ones, and then I will have the vector that goes from C to B crossed with all the forces that act there. Make sense? That's the definition of M. Well, the general definition is summation, start from there if you want, Ri minus R bar in this case crossed with Fi's. And now Fi's are, well, F on A is, again, only the external ones, is going to be mg, well, with a minus EY, that's gravity, right? Plus some NA that I don't know, EY as well. I'm just writing the components here that I need to plug in the M bar. And then F in B, same force of gravity, just because they have the same mass. But if that wasn't the case, you wouldn't have to be careful that the masses could be M1, M2. Plus, now for B, I have a reaction that goes along the EX direction, right? If you want, I can do the free body diagram here. This is mg, this is n on B that I don't know. And remember, there is always this F acting on B due to the fact that there is A somewhere else, so the internal forces, but this doesn't contribute to that moment of forces. They are only external ones. And so I have NB EX. And as you can imagine, these things will not go away, because I'm going to cross, for example, in the case of A, I'm going to cross this vector, which is NA, the reaction from the ground, with the vector that goes from C to A, In general, that's not 0. And the same between the vector that goes from C to B and n in B is not 0. So believe me or not, what you get in the end is, see what I have? The final moment is L over 2 sine of theta n A minus L over 2 cosine of theta n B. I don't really need this H to be here anymore. Okay, and B, this is all about the easy axis, on the easy axis. That's what I get. Again, I invite you to do it. All you have to do is compute RA minus R bar, again, cross with FA plus RB minus R bar cross with FB. Go through the cross products, and you get that. So my final equation of motion is equating these two terms. So I can just move these down here. I have L squared theta double dot over 2 EZ equal that. Not very nice. I mean, it's a perfectly legit equation of motion. It's just that an A and an B, I mean, unless you do it numerically, you have initial conditions and all sorts of other stuff. I mean, by itself, is not, you can't solve it. I don't see just theta, theta dot, theta double dot, and constants there. There are these two magnitudes of the reactions that I don't know. And I may not care knowing them. And so how would you do it at this point? If you had picked that point, which is a perfectly fine point to pick, but it's probably not that convenient, what would you do now? No, you can actually finish it this way. I mean, of course, there must be a way, but the way I finished it is, unfortunately, the angular momentum equation is not enough. I have to use something else to eliminate an A and an B. While if you do with Q, which you guys are going to do at home, you promise you're going to do it. If you do with this point up here, as you can imagine, that NA and NB are going to point to Q, so those cross products will go away. But you have to take into account the term R bar minus RQ cross with MAQ in N, which is fine. It's better to have that than those. Well, the way I did it is, well, that's the equation we get, and that's fine. It's there. I'll leave it there. Is what would you do? Say that you're here. You don't want to go back. You don't want to solve everything again. Yeah, which is a system of particles, though. Meaning that M, yeah, in my notes I wrote, what did I write? There should be 2M, right? 2M A bar in G is going to, so I'm looking at the entire system now, right? So if you want, this is the free body diagram. This is B up here, right? B, A, point C, I have 2mg, and then I have NA and NB. And that's it. Those are the external forces. So 2mg plus NA plus NB. And let's see if this helps me in any way. It should. See what I have? I have 2m acceleration of center of mass if you do it from, derive these twice with respect to time. It's L over 2 theta dot cosine of theta minus theta dot squared sine of theta Ex minus L over 2 theta double dot sine of theta plus theta dot squared cosine of theta. I know for once I'm not doing all the steps, but this is really things that at this point you must be able to do by yourself. I'm just giving you the final expression to make some comments. Plus, oh, I'm sorry, I want to write these already. in the coordinate system, so this is big EY. NA is along EY, we said, and NB is along EX. And so if I look at that expression, and at this point I can probably erase everything here. Yeah, let's be careful. Let me write it down here. Now I start seeing the light, maybe. So on EX, on the right-hand side of this equation, I see only NB, right? So I get that NB is equal to, that's the magnitude, to what is multiplying EX here, which is that 2m, well, it's ML, simplifying the 2, ML theta double dot cosine of theta minus theta dot squared sine of theta. And that's it. And the same I do it for, well, NA plus, well, the gravity is a known force, so I have NA equal to 2mg if I bring that on the other side, minus ML, all that thing there, theta double dot sine of theta plus theta dot squared cosine of theta. You following here? The coordinate system is an orthonormal basis, so I can do this. I can equate, the components along the different directions. So now you can take these expressions that are very nice. They are functions of the theta angle, its first time derivative, its second time derivative, and known constants, and substitute in that equation, and that will give you your final equation of motion, which here involved not using only the angular momentum formula, but also this one. So what's the point of starting the problem with the angular momentum? It's really a huge pain. The point is that by itself, it didn't help me. While it could have helped me to get the final equation of motion picking this point. You would have been done by just using the expression of d dt of h with respect to generic point q, the full-blown equation with respect to this point. The reactions will go away. And if you think about what we've done with a single particle, that's really the point of angular momentum. It's an alternative to F equal ma or to this equation, but you have to use the alternative wisely, otherwise it's not an alternative anymore. It's just making you solving the problem actually longer. Okay? Questions on this? So I invite you to redo this, all the steps, because I'm giving you here the final answers of doing all those cross products, etc. But do it yourself. It's really just a couple of pages. And then do it with respect to Q. If you want, I can give you the equation of motion I get. Well, I don't have it actually. I stopped here. I just noticed that it was done. There were no unknowns, and I said, okay, I'm happy here. Which is really the point. You want to find an expression that is free of the reactions, so you can say this is my equation. But anyways, you should get the same thing. It's pretty ugly, as you can imagine, because once you substitute these NA and NB there, it's not going to be very friendly, but that's what it is. Okay. Now, it is time to move on, unless there are any questions, because, yes? Here or here? So L squared, there is a squared missing somewhere?
No, M on the left side.
The mass is missing? I don't know, could be. Dimensions are not matching. That's a good check. So this has dimensions that are not matching? It could be. Let me see. Okay, so these are forces. This is 8-dimensional. This is a length. So this has a dimension of newtons times distance. Right? Why is it not matching? What is the dimension of this? This is, say that we're doing meters. It's a length squared over time squared. Oh, I see what you mean. Did I miss any product at some point? It could be. Whoa, I think I left out, I may have left out a mass somewhere, right? Yeah, I think it's, yeah. Oh, I erased that for me. I'm sorry. I think there is an M here, right? On the left, yeah, on the left side, I'm sorry, yeah. Yes, thank you. I left the M out. Yeah, I had the cross product with the M, and then the next step, it just disappeared. I simplified it. Just made my life easier. Okay, so correct your notes. The H, the actual, do we need this? I don't think we need it. Thank you. The actual H, yep, H bar in G is ML theta dot squared over 2 EZ. Make sense? And so the dt of these as an M. Yep, thank you. I just disappeared from one step to another. So this is an algebraic error that you would pay on a test a few points, but yeah, it's not a conceptual error though. It's not you applying the expression, the result incorrectly. So that's what it is. Okay, so let's move on. Anything else? Okay, next time we'll start seeing kinetics of rigid bodies. And to do that, we need to refresh, I guess, for some people, you may have seen it before or not, the concept of tensors. And I'm going to briefly touch on them, and then we'll use them next time. There is sections in your book that you must study about tensors. Okay, so we said, what is a vector? When we started, we said a vector is a quantity with magnitude and direction. We said vectors do not care about reference frames, do not care about coordinate systems. They just exist as objects in 3D Euclidean space. In some cases, the reference frames matter when you take rates of change, but the results are still vectors, and those are coordinate free. Now, tensors are, let's define, let T be what is called the second rank tensor. All we need to do about tensors, they are also geometrical quantities that do not have anything to do with reference frames and coordinate systems. They are coordinate free. And all we need to know is that T is a linear operator that takes vectors as inputs or input and returns vectors as outputs. And we say that, for example, C, which is a vector, can be generated by applying, this means applying the tensor or operating the tensor on C. I'm sorry, this is another vector, B. Operating on so B will be the input of this tensor, which can be any sort of operation. I mean, there are, we'll see one case. The cross product is actually a tensor, can be defined as a tensor. It's a linear operator that takes a vector and gives you another vector. So in general, that's what it is. Second rank tensors, there are higher ranks tensors if you like, but we're not going to use them. For what we are concerned is there are geometrical objects that take a vector B and return a vector C. What this T is doing could be many different things. It could be just changing the magnitude of B. It could be taking B and actually rotate it, change it to a different orientation and change its magnitude. It could be all sorts of things. The fact that it's linear means that when I apply T to alpha 1 B1 plus alpha 2 B2, etc., it is the same thing as doing A1 alpha 1 T operated on B1 plus alpha 2 T operated on B2, etc., if you had more of them, right? That is the definition of a linear operator. That's all we need to know. It's a linear operator that takes a vector or several vectors and returns a vector. And we use them. Now, we use them in different ways. Okay, so we need another definition here. We define tensor product. And I'm only defining things that I'm going to use next time, just the things that the tools that we need between two vectors A and B. We indicate this product with the circle cross. This is not a cross product. This is a circle cross. And this is actually the definition. So it is defined through taking this cross product and doing the, I just made that mistake. The tensor product between A and B and doing the dot product with another vector C, B dot C A. That's just the definition. That's how it's defined. We use it. We'll need these tensor product definition. Now, what is this that I have on the right hand side? What is it? Is that a scalar? So it is a vector. Okay, so tensor product between two vectors is something that returns a vector.
Are you writing tensor as T double underbar or
T double underbar. T double underbar, yes. So that's indicating the second rank. So if a vector, if you want, is a tensor of rank 1. So it lives on a higher dimension than vectors. Well, we can see vectors in 3D Euclidean space. You cannot see a tensor, right? But so that's double underscore will indicate a tensor from now on. I don't know how it's indicated on your book. I think a vector is bold and a tensor is, I don't know. I just cannot do bold or other stuff on the board, so that's what I will do, under double underscore. Now, what we need to understand is that T is, I'll just do a quick example here, or just, we'll think about a couple of examples. A tensor is, as a vector, completely independent from reference frames, coordinate systems. Is an operation that exists no matter how you represent it. The same way you take a vector, you represent it in a given coordinate system, that's just a representation of the vector. It doesn't change the vector itself. T also can be represented in a certain basis, but it doesn't change T. And what do I use? I don't remember. Capital letter, right? Okay, so capital letters bold its tensors in the book. Yeah, makes sense. They cannot do it double bold, I guess. Yeah. So the few comments I want to make are the following. You've been used to here in this expression, I believe, and I've used it a lot as well, rotation matrices, right? You've heard this. Well, let's start from a vector. If I give you three numbers like this, we said this at the beginning. What is this? These are three numbers. This is not a vector. It is a vector if you tell me that this is how the vector A it's expressed in a basis, right? Then it becomes a vector. The numbers by themselves, they don't tell me anything. Now, say that I have another basis now. What do you want to call this? A1 prime, A2 prime, A3 prime. And this is the same vector, but it's now expressed in some other basis, U3. You cannot do this, right? They're not, you cannot just say equal to, because they are three different numbers. These are already, this is not coordinate free anymore. I picked these bases, and you guys picked these other bases, and for you, the vector expressed in these bases corresponds to three numbers, 1, 2, 3. For me, corresponds to, I don't know, some other numbers. So what you've seen in the past is something here that allows you to go from the representation of a vector from a basis to another, right? And what did you call that?
We call it rotation matrix, transformation matrix.
That's a transformation matrix. It's not a rotation matrix. It doesn't rotate anything. That's the point. You're not rotating anything. So I don't know what I called it here in my notes. Let me just be consistent. I think it's probably consistent with the book. Some V matrix. I don't know. A matrix that goes from U. Well, in this case, I go to U. Yeah, U to E. But anyways, there is a matrix here in between, which is a transformation matrix. You're not rotating anything. It's the same vector. The vector in 3D Euclidean space, you're running around like crazy, define coordinate systems, reference frames, and you have all sorts of three different numbers. But the vector is just there. It doesn't care. It's always the same. So you're not rotating anything. You're not changing the vector. You're just picking ways to represent it. You're taking pictures of the vector from different perspectives. That's really what you're doing. Nothing else. So there's no rotation matrices. There are transformation matrices that go from a basis to another. That's all they do. There are rotation tensors. A rotation is actually taking this vector and rotate it maybe. In that case, you talk about tensors, right? So one operation that you may be performing is taking a vector B, and you don't change its magnitude, and you just rotate it in 3D Euclidean space to a new vector B prime about some axis with a certain angle. Now this is B prime is going to be some tensor operation applied on B. Now B and B prime are two different vectors. Now this is a rotation. It's just an abuse of terminology. A tensor can be represented as a matrix once you pick a basis. I'm going to see the case of cross product, but that's what happens. When you pick a basis, then you can represent the vector with a matrix, but the tensor with a matrix, but that's just a representation. The same way these two are representations of the same thing. They don't change the vector. Okay, so what I want to prove, real quick, is the following. Again, these are just tools, and I invite you to read the section on the book that talks about tensors, because we're going to use them. And all we need to know about tensors is really what I told you today. But I want to prove that, is this a tensor? So given a vector A, crossing A with some other vector, is it a tensor? Well, what is the sanity check? 1 is doing this, taking a vector as input and giving me a vector as output. So let's say vec in and vec out. Yes, check. When I cross A with B, I get another vector C, which is a vector. Is it a linear operator? Is it? A cross with alpha 1, B1 plus alpha 2, B2, and I could go on forever, but I don't want to. This is equal to alpha 1, A cross B1 plus alpha 2, A cross with B2. It's true. It's one of the properties of cross product, so that's check. Do I need anything else? That's it. So the cross product is a linear operator. And you may have seen that, that a way to represent cross product is once you pick a coordinate system, is through a skew-symmetric matrix. Have you ever seen it before? So that's already representing the, so let's actually do it. So let's say that we have vector A, which is now, having picked a basis, is A1, E1 plus A2, E2 plus A3, E3, and then I have the other vector B, which is B1, E1 plus B2, E2 plus B3, E3, and then we compute A cross with B, and now this is going to be equal to, we do it one by one. What is E1 cross with? So this is A1. I'm going to do E1 first. E1 cross with E1 is 0, so A1, B2. What is E1 cross with E2 is E3. Then I have A1, B3. What is E1 cross with E3? Minus E2. That's done. Second one. So I see an A2, B1, but then E2 crossed with E1 is actually minus E3, right? So let's put a minus here. So I've taken care of this. This is a 0. Then A2, B3. And what is E2 crossed with E3? That's E1. And I'm not done. I have the last one. I see an A3, B1. What is E3 crossed with E1? E2 with a plus. And then the last one, since this is going to be 0, is A3, B2. E3 crossed with E2 is minus E1, right? OK. So when I collect all the terms that have the same component here, so I have E1 that is multiplying what? Help me with this. No, that's the one. A2, B3 minus A3, B2, right? Then I have E2. Let's see, I have this. A3, B1 minus A1, B3. And then I have E3 down here that is multiplying A1, B2 minus A2, B1. Is this coordinate free? It's a tricky question. But these are vectors.
As long as they're in the same basis, you just need to discard them.
But this is E1, 2, and 3 are vectors. So if those are vectors and I'm summing up vectors, this is still coordinate free. It becomes not coordinate free when you just write the components. Those are not coordinate free, right? When you decide that the numbers themselves, once you use those, you can't. So there is a way to write the cross product which is done the following way. This is not coordinate free anymore. This is already the vector in E. And then you populate this matrix. So let's do it. There is a bunch of zeros here, believe me. You can double check. And then the first one is going to be what? Minus A3, A2 here. Second one is A3 here. And then I have a minus A1 here. And then I have, what do I have? B2. I'm sorry, no. A1, right? A1. Yep. And then minus A2, right? That's your skew symmetric matrix. It's symmetric, but then the signs are.
A1, A2, you switch.
Yep. Yeah, makes sense. Okay, now it's skew symmetric. Yes.
And positive A1.
And the plus
And positive A1. Yes. Okay. That's your matrix. So if you want, this is now a representation of the A cross tensor in this basis. Because I picked that. So once you put things into brackets like this, now this is not coordinate free anymore. You are stuck with the coordinate system you picked, which is E1, 2, and 3 now. So now this is stuck. It's you know, you have to deal with that. You pick that coordinate system. But the operation of doing the cross product, it's completely coordinate free. It gives you a vector. It takes a vector as an input, gives you a vector as an output. So by definition, it must be coordinate free. The tensor itself can be represented as a matrix once you pick the coordinate system. Make sense? So it's really not that different from vectors. It's just that you cannot visualize tensors that easily. I cannot really, look at them as lines and arrows in 3D Euclidean space, but they do exist and they do operate on other vectors and give you vectors, and they're linear operators. That's all we need to know.
Have AX right here, have the A underlined, there's A factor.
Thank you. Making a lot of mistakes today. Yeah, that's fine. So, but yeah, that's the point. The matrix can be, the matrix by itself is a matrix. It's a bunch of numbers inside brackets, but it can be a way to represent a tensor in a certain basis. So we do need this because we're going to start rigid body kinetics next time, and we'll have the inertia tensor, not the inertia matrix. If you think about it, the inertia tensor, the inertia by itself, rotational inertia, is a property of rigid bodies. It does make sense that it's reference frame coordinate system free, because it is a property of a body. How can that change with you changing your point of view? If I'm looking at that bottle down there, it's resistant to change the rotational motion, which is the inertia tensor, represented by the inertia tensor. Why should that be different? Because I look at the bottle from here or you look at it from there. It shouldn't. It's a property of the body. So that's why we'll talk about inertia tensors, not inertia matrix. That's the right terminology. And so we will need tensors. Please do go in your book and study them a little bit. And let me know if you have questions. But that's all we need. OK, thank you.